video quality is so-so on this. There's a reason for that, because I want you coming to class. Right? This is not supposed to give you like, oh, he's recording the lecture, I guess I never need to come again. No, the point of this is in case you happen to miss class, or if you want to review something in a couple weeks, you're like, oh, I didn't really understand the fundamental theorem of arithmetic, I better watch that again. You can do that, but this is not intended to be a replacement for coming to class. But I stopped recording the lectures when COVID ended, and I came back, and the students were really telling me, oh no, we really want to keep having those videos there. And I've been continuing to do it, and people have said that they like having them, even though, like I said, they're just sort of, sometimes I forget to turn the camera to the other board, and you have to just listen to my voice. I mean, I don't claim to be a professional videographer by any means, but anyway, it'll be there. Yeah, so what was I saying? Yeah, I just spot checked or picked a couple of the results here that we will be using today. The two theorems that you see in chapter 2, which is kind of just an introduction to divisibility in number theory. 2.3 is actually, this first theorem has been used on Putnam problems. It's not, so the Putnam exam is one of those, for those of you who don't know, is this really competitive and challenging math competition. And it often requires quite a bit of creativity. You sort of have to pull things out of the sky from some maybe unnatural places to solve problems. Well, this particular theorem is kind of not the first thing you think of when you're thinking about the greatest common divisor of two positive integers. So here we have two integers, I said positive, two non-zero integers, a and b, which is that the greatest common divisor of a and b can be expressed as an integer combination of those two integers. So there exist two other integers, x and y, such that the greatest common divisor of a and b is ax plus by as an integer combination. Now, this is not unique. The x and y here are not unique. I think I mentioned that when I talked about this in the video. So keep that in mind as well. But that's a useful fact. We're going to use it even today in something that we're about to do in a few minutes. So I wanted to remind you about that result. I don't particularly care that you memorize numbers of theorems. I put them up here, of course, so that you can keep compatible with the book. But whenever I know a name of a theorem, like Euclid's lemma, I will write it that way for you. But otherwise, my best way to refer to them is through the book's numbers. Euclid's lemma is another really important one. We're going to use this one today as well, which is that if A divides the product of two numbers, BC, and if A and B have no common factors, that means their greatest common divisor is equal to 1. Well, that would mean that all of the factors of A must be buried or embedded inside of C. So A actually has to divide the integer C in that case. It's kind of common sense that that would be the case, but it's good to lay it out as a lemma and write it in a careful notation like that. So these two results will come up in just a little bit today as well. I mentioned that you might think of number theory as being a theoretical type of subject, which it very much is, and I'm a theoretical mathematician, so it kind of makes sense, but there's a lot of applications to it as well, and I would like to spend the first part of today's class anyway, talking about some of the applications of number theories, or at least one very important application of number theory. By the way, I get really excited about math. If I am talking too fast or going too fast, it's not because I'm trying to like blow you away. I'm just like on a hyper kick. It's like my caffeine. It's like, I don't know, I just go. So just slow me down. Just ask me questions. I'm so open to that. And that will sort of bring me back down to earth. I'll kind of pace the thing out a little bit better. So don't hesitate to interrupt here, guys. This is not, I know sometimes I come across as being fairly formal in the way I do things. That's just the way I am as a person. But I am so casual about like slowing down, making detours and trying to answer questions along on the side. So please don't feel bad. And if you've got a question about something, I can guarantee you there's probably multiple other people in the room with the same or very similar question. So no need to hold back on that kind of thing. But let's take a look at this next section then, now that you guys have already watched the videos on sort of the introductory part of number theory. 2.5 is titled the Diophantine equation. Kind of a mouthful. The Diophantine equation, AX plus BY equals C. So here's what we're going to talk about first today. And the goal here is, well, I'll write this as a goal. Kind of what we're going to be trying to do with this is if we are given the fixed values, well, these would be fixed integers, A, B, and C. The goal is to find solutions for what are kind of viewed as the unknowns here, which I'm going to call as X and Y. And I'll add if possible. So when you have a Diophantine equation, the goal would be to try to find the solutions for X and Y if possible. So not every Diophantine equation will have a solution, and when I say if possible, I should add with X and Y being integers. With X and Y being integers. So I'm looking for integer solutions here. Everybody probably knows that this equation, AX plus BY equals C, is just the equation of a line that you could draw in the XY plane. Well, a line has infinitely many points on it. Well, that means that this equation, if we view it in the real Cartesian plane, is going to have infinitely many solutions. There's no mystery about that. But if we're requiring our solutions to have integer whole number values, now it's kind of a different game. Instead of thinking of the whole XY plane, if you want to have kind of a visual of this, what you have is a lattice of just the integer pairs of points. So we got our XY values laid out in a traditional Cartesian plane like I'm drawing right now. But we are looking for solutions to this equation that actually have integer values, meaning that the solutions should be on one of those dots. So if I draw some line through here, right, it might not be clear whether that line ever hits any of those dots, those like individual points of this lattice where you have whole number coordinates for both X and Y. Does everybody kind of see? Like this problem is maybe not interesting on the level of calculus, if you were solving it as a calculus student in the real numbers, it's not very interesting. But if you're thinking about it where you're looking for solutions that are on these lattice points, now it's a much more interesting problem. And it might be that you're solving a physical problem that has to have whole number solutions. X could represent the number of adults, and Y could represent the number of kids. Well, you're not going to want to have fractions numbers of adults and kids solving a problem. So, right, question. So are we talking about integer solutions? Integer solutions. I use the word whole numbers and integers kind of almost interchangeably. I know that technically some people will require whole numbers to be positive. Right, but I'm using it more loosely, that they basically just don't have any fractional pieces to them. Yeah, good point. Sometimes the language needs to be clarified. But yes, in this case, you might have a physical problem where X and Y should be whole numbers for it to make any sense at all. And so you'd be asking, well, is it possible to find solutions? So just as an example, maybe I'll draw an actual example here of a Diophantine equation. EX just means example. What about 6x minus 9y equals 7? We'll start with something concrete like that. And we might ask ourselves, are there any integer solutions for x and y here? Does anybody have any thoughts about that? Think it would be possible to find values of x and y that would make that equation true? You're shaking your head no. Why not? Okay, so basically, the thing on the left has to be a multiple of 3. Because 6 is a multiple of 3 and 9 is a multiple of 3. So unless you're going to go into the realm of fractions, right? What you have on the left side will always be a multiple of 3, no matter how hard you try to choose values for x and y. And so there's no way that would equal 7, because 7 is not a multiple of 3. So this has no integer solutions. Now, when I say no integer solutions, I mean both x and y cannot be integer. I mean, you could choose one of them to be an integer, but you can't make both of them an integer at the same time. In other words, you will never find, this line will never cross or never intersect with that lattice that's on the board there. Okay. Now, if you want a quick little reason, the reason is essentially what you just gave. What is your name, by the way? Okay. Kim? Okay. So this is just since the GCD of 6 and 9 is equal to 3, which does not divide 7. Okay, so in that case, there would be no solutions, more or less for that reason. Clear enough? It's because 7 is not a multiple of 3, basically. But, you know, it's very easy to just tweak your example to get a completely different result. If I had 4x minus 6y equals 10, well, now the left-hand side, it looks to me that you'll always get an even number, but 10 is certainly achievable as an even number, and this does have solutions. Has solutions. Anybody want to give me one? Tanner?
A 1, -1.
1, -1, right? Okay, is that the only answer? Marcus?
X equals 4, y equals 1.
4, 1, that would also work, right? And in fact, we could keep doing this and come up with lots of answers, right? I don't want to try to list them all. And in fact, there exist infinitely many solutions. Right? So this is actually fitting very nicely in with when you have a system of equations. Okay, so I'm changing topics for just a moment. Linear algebra. If you have a system of equations in the real numbers, right? So now we're not in integers, we're just in real numbers. Every system of linear equations, I hope you've maybe learned this in linear algebra, we will either have no solutions or infinitely many solutions, which this example does, or it will have exactly one solution. So you have those kind of different scenarios. So this is starting to feel like that could be the same case. Actually, in this case of a Diophantine equation where you're looking for integer solutions, you will either have no solutions at all, like the first example, or that equation will have infinitely many solutions. There are no other options. So it's either all or nothing in that sense. So I think actually we're probably already in a position to state a theorem that I don't think you will be too surprised by. And I'll do it over here just so I have a nice clean place to start writing it down. But let's write down the first theorem that is basically motivated by these two examples. And then, of course, we won't get away without doing a proof of that. Before I get to that question.
Or GCD is only 1, then would we automatically have infinitely many solutions?
If the GCD of A and B, which is in this case 6 and 9, here it's 4 and 6. If that GCD is equal to 1, the question was, will we automatically have infinitely many solutions? This theorem is going to answer that question, but the answer is going to be yes. Yeah, it will have infinitely many solutions in that case. So really, really good. Some good conjecturing going on out there in your heads, I think. Let's state the actual theorem here. This is theorem 2.9. And it just says that the equation ax plus by equals c, where a, b, and c are integers, has a solution So at the moment, I'm just asking, does it have a solution or not? I know you're wondering, well, how do you find the solution? We'll come to that next, but whether it has a solution or not, there is a nice characterization of this as an if and only if statement. And a lot of you are already kind of hinting that you have an idea about this, which is that you are going to look at the greatest common divisor of A and B, and you're simply going to ask whether or not it divides C. That's the statement. Okay, so if the GCD of A and B divides C, then the answer is yes, it has a solution. So that wasn't the case for the first example, but in the second case, you know, the GCD of 4 and 6 was 2, and 2 does divide 10. Right? So, okay, so this is pretty reasonable. I would like to do the proof of this theorem for you. I'm generally not going to skip proofs in this class. Kind of one of the important hallmarks of a theoretical class like this, so you will get the proofs. And because it is a biconditional statement, I must prove it in both directions here as we go along. So let's do the forwards direction first. So let's just assume that AX plus BY equals C is valid for X and Y in the integers. So let's suppose that we do have a couple of integers X and Y such that AX plus BY does in fact equal to C. Let's assume that that is true. And so my solution, by the way, the solution should really be thought of as an ordered pair. It's the pair X comma Y, right? So, but I'm not really writing it that way. I'm just putting it into the equation as being valid here. And what I want to show is that the greatest common divisor of A and B would have to divide C in this case. Okay, well, this is really quite easy to do. So then the GCD of A and B, we know that it divides A because the GCD of A and B is a divisor of A. And if it divides A, it would divide any integer multiple of A as well. So I don't know if you remember some of my basic properties of divisibility from the videos, right? So if the first one divides the second one and the second one divides the third one, well, then the first one divides the third one. Everybody with me? Right? And then similarly, we could just start all over with the GCD of A and B. It obviously also divides B, which means that it also divides BY. Okay? And as soon as a common number divides two different things, it would divide any integer combination of those things, including AX plus BY. Okay, so by basic properties of divisibility, I'll just kind of use that as a catch-all for this proof. By those basic properties of divisibility, the greatest common divisor of A and B is now going to divide AX plus BY, and of course that is C. So that's your forward direction proof in a nutshell. Nothing too hard and heavy about that. Does that make enough sense for folks? Everybody okay with that? Okay. Let's reverse direction on this. The backwards direction is a little bit more interesting. So we need to assume that the greatest common divisor of A and B divides C, and then from that, we need to convince ourselves that there would be a solution to the Diophantine equation, right? And actually, the way the proof is going to manifest itself is that we're actually going to produce the solution in the proof. So it's not only proving that the solution exists, it's going to tell us how to get it. So that's kind of the nice extra power that this backwards direction of this proof is going to have. So I'm assuming now. Well, actually, before I get into it, let's just use D to represent the greatest common divisor of A and B. I actually think that notation will be helpful. And so let's assume that D divides C. Okay, because I'm proving the backwards direction. So I'm assuming here that D divides C. Let's just write down what that means. That means that there exists an integer, call it M, in the integers with C equal to DM. So that would be just the definition, more or less just the definition. We, of course, had that in the notes last week as well. So C is just going to be D times M. And now is where I'm going to use the fact that the GCD of A and B can be written as an integer combination of A and B. That's theorem 2.3. So starting with A and B, we can use theorem 2.3. So I'll just say start by theorem 2.3. There exists integers X and Y. Guys, please be careful in your write-ups that you're specifying where these elements exist. Don't just have M's and X's and Y's showing up with no quantifiers, right? I want to know that these are integers. Most of the time, yes, the notations that we're using are going to be representing integers, but it should not be assumed without writing it down because there will be exceptions, and it's just good practice to always quantify your variables. So there exists integers X and Y with AX plus BY equal to C. Okay. So we've got, I'm sorry, equal to D. Sorry. D, yeah. Equal to D. I want it to equal C. Thinking ahead a little bit too much. Well, I can make it into a C by just multiplying through by M, which is what I'm going to do next, right? So multiply through by M, and what you'll get is AM X plus BMY equals, well, I'll just write it as C. It's D times M, but that becomes C. And so it looks to me like we have our solution here. A times something plus B times something is equal to C, right? So MX comma MY is a solution. So here I am writing it as a pair, right? MX comma MY is a solution to the equation. Yeah. This is a classic example of proving the existence of something by actually just producing it directly. Can't always do that in math. Sometimes we get these abstract proofs where you prove the existence of something, but you have no idea how to find it. That's not the case here. We can literally find it because remember, the M, the X, and the Y are all going to be findable using the setup of this assumption here. So there won't be any question about that. Now, I did make the point, though, that there isn't just one solution. And actually, the reason for this is that the X and Y over here, when we were talking about this theorem, there was not just one solution for X and Y. So that's why you'll get many different solutions here as well, okay? The M is unique, of course. The M is unique, but the X and Y are not, right? The X and Y are not going to be unique. But it is nice that this is a constructive proof. It constructs the solution right there for you. But I do want to talk about how you would then generate all of the solutions. It turns out we can create an algorithm for finding every solution to our Diophantine equation in the case that there is a solution. Okay, so let's make this as a remark. So I guess I'll put it right here. So once we have a solution, let's just say X naught comma Y naught for our Diophantine equation. All right, so once we actually are able to make a solution for our Diophantine equation, all other solutions, kind of underline that, that's kind of the key point here, all other solutions will have the form we'll be able to write down where they're coming from and how they look in the following way. Gonna do this as a brace, I guess. So the X and the Y values that will give us other solutions can be kind of enumerated. And the way we do this, guys, is we take, for the X value, we take X naught and we add B over D times T. T is going to be a parameter, very much in the traditional sense of parametric equations in calculus, right? So T is just going to be over here. I'll just add T is going to be some integer, right? And then what about the Y value? By the way, this is something you're going to want to write down. Probably going to want to memorize it, to be honest. So the Y value is Y naught. And then in this case, we have actually a minus A over D times T. So you kind of have to memorize this a little bit, where the A and B are and where the plus and minus go, but it's nothing too crazy. It may look like I'm doing fractions here, but not really, because D already divides A and D already divides B. After all, D is a common divisor of A and B. So you're not really delving into the world of non-integers at all. But basically, you can just choose values of T as long as you want and come up with more and more solutions. This is why I said, as soon as there's one solution to your Diophantine equation, there's actually going to be infinitely many. And they are all calculated that way. Probably should prove this as well. It's only a remark, but it deserves to be explained a little bit. Question first.
Can you interchange the plus or minus?
You should. No, I think you should. I think they need to be left like this, because if you interchange the plus and the minus, I mean, you could replace. Interchanging the plus and minus would be essentially replacing the A and the B with negative A and negative B. And that doesn't satisfy the same equation. The equation, if I interchange A and B with negative A and negative B, I wouldn't get C anymore. I'd get negative C at that point. So, but this is not a unique expression for how to express this solution, if that's what you're wondering. There are multiple ways of doing it. Yeah, Matt?
It's sense and also just a reflection of T. So
Yeah, so you could replace T with like if you switched the notation here, you could change T to negative T and maybe re-parameterize it with a different variable. Is that kind of what you're suggesting?
yeah, sure. But
Yeah.
I guess what I'm asking is, like, if we can't switch the plus and the minus sign, that kind of suggests that T can be negative. Is that true?
So you are right. So I see what you're saying. So if let's say I plugged in T equals 3 and I had a solution for X and Y, then if I wanted to, I could replace T with negative 3 by changing the B to negative B and the A to negative A, which would effectively switch those signs. So I think I stand corrected. I think you're right, actually. I think you're right. I could, but they need to be opposite signs.
Yeah.
Is the key thing. Yeah. So you're right. We could tweak this a little bit. It's kind of a arbitrary choice, I guess, in that sense, whether you put the plus here or the minus here. But I stand corrected. I think you're right. Because the T is allowed to be positive or negative, that does make sense. Okay. Yeah. So anyway, but this is the way I'm going to present it. You want to do your own form of it? That's totally good with me. Let me try and write down the proof of this remark. That this actually works, and then I think we'll be good. So it starts off by saying, once we have a solution, well, X naught, Y naught is my solution. So that means I'm assuming that A X naught plus B Y naught already is equal to C. And so then I want to just check whether any of these X and Y expressions would also work, right? So I'm going to actually, this is just proof by plugging it in. I'm going to take the X that I have here If only they were always this easy. You just plug in what I replaced the x with, which is x naught plus b over d times t, and then plus b times what I replaced the y with. I'm going to replace y with y naught minus a over dt. And I'm not going to say equals c yet. I'd like to determine whether that still works. Does it still satisfy the Diophantine equation? Well, if you do the math on this, it won't take you very long. Ax naught is here. By naught is here. And the other two terms cancel. If you notice, AB over D times T, and then minus AB over D times C. So that goes back to the point that you do need to have one of the expressions positive and one of them negative to make them cancel out like that. But the point being that you end up, sure enough, this does equal C. This does equal C. So once you found this solution, if anybody was ever questioning how many solutions would you have, we now know there are infinitely many, parameterized by the variable t right here. Yeah, and we can check it right now that this is really true. So this was the x and this was the y that we wrote down just a moment ago. Yeah. Now, actually, what's up there on the board right now is not really the interesting part of the remark. The remark says that all of the other solutions must have this form. That's actually not the same thing as what I've proven right now. What I have proven is that anything of this form will be a solution. But what I have not yet proven is that there will be no other solutions out of the blue that somehow look different than these. And that I also would like to prove. So I'm not really done proving my remark yet. This is just the first step. Yeah, question.
So being a little bit out of topic, but let's say
Okay.
you were to get your x, or no, you were to get your y divided by x, and then let's say you had some y equals, let's call it q times x plus r,
Mm-hmm.
and then you replace y with that equation and x with that equation. Would you get a Cartesian equation with what do you call it, with integer solutions?
Can I chat with you about that a little bit later? I'm not quite sure I kept up quite with what you were asking. I know you're doing like the division algorithm with that. You're taking a solution x and y. You're dividing x by y with some quotient and some remainder. I think that's what you're doing. Yeah, let's talk about that maybe after class for just a couple minutes. I want to write it down. Yeah, this is a good question. If I come up with anything in the meantime, I'll let you know. But yeah, I want to take an arbitrary solution to my Diophantine equation and prove that actually that arbitrary solution must be of this form. That's actually the more tantalizing part of this remark. It's the more interesting part of this remark. So let's write that down over here. And this is going to take a little bit longer to justify. Right, so let's do that over here. So now suppose that, let's say, I'll write it as an ordered pair again, R comma S is an arbitrary solution to the Diophantine equation. It's an arbitrary solution to the Diophantine equation, meaning, of course, that what that means, if it's an arbitrary solution to the Diophantine equation, it just means that A times R plus B times S is equal to C. Let's imagine that. What I would like to show is that the R and the S must have this form. Okay, must have this form. Okay, so let's do the following. Let's find an integer t. Okay, I'm going to find an integer t such that x naught plus b over d times t is equal to r. Now, what I'm really doing there I had to stop and pause at this moment. I had to stop and pause about this, but I've already got this solution. And now I'm assuming I also have this solution. I have two solutions. I have the X naught, the Y naught, and I also have the R and the S. And so I know what this number is, and I know what this number is. Of course, I know B, of course, I know D. So I'm just solving for T right here. Actually, if you wanted to know what T is equal to, it's just, it says find T. How do you find T? Well, it's really just R minus X naught divided by B over D. Okay. Is anybody bothered by that at all? Because I was. Yeah, are you bothered by
I'm
it?
just, wondering how we can make sure T is so an integer.
How we can make sure that T is actually an integer. I mean, according to this formula, you don't need to write this down, I'm just kind of scribbling for a minute. But according to this formula, it looks like T is R minus X naught divided by B over D. Right? If I solved for T, that's what it would be. And that sure isn't clear to me that that's an integer, but that's what was in the book. So I had to stop and do a little pondering about it. Let's put an asterisk next to that, because in a minute, I'm gonna exactly answer Marcus's question, and I will show you that it is an integer. It's not clear. It is not clear to me, at least, that this is an integer. So I'll come back to that in just a second. But let's say that it's going to work out and that we can find this integer T. At that point, it becomes very easy to finish the argument that I'm trying to make. First of all, you'll notice that the R is already in the right form. It's already X naught plus B over D times T. The only question is, well, what about the S, which was the second variable? Well, let's just see if we can figure out anything about S. We would like S to be this one. Well, let's just check it out. What do I know about S? If I solve for S here, it's going to be C minus AR all over B. So I'm just solving for S in this equation here, right? So I could certainly do that. And since I've already worked out what R is, I could just feed it in here. So this would be C minus A times whatever R was. Well, R was X naught plus B over D times T. And then all of that is still over B. Like so. And let's try and clean this up and simplify it a little bit. Remember, guys, X naught, Y naught has to satisfy our Diophantine equation. Right? Has to satisfy our Diophantine equation. I actually see C minus AX naught over there. Take a look at the numerator here, guys. C minus AX naught can be replaced by BY naught. And then we have plus, actually it's going to be minus AB over D times T, and then all of that over B. Still all over B. So this part right here becomes BY naught by that circled equation at the top. The rest of this is just like multiplying it out. The A times the B over D times T, that's just right here. All over B. What you notice, I hope, is that there's a B everywhere. If I cancel the B's from everywhere, I have Y naught minus A over D times C. There's B's upstairs and downstairs. They're both the numerator and the denominator. If I factor and cancel the B from everywhere, I just get this. And my friends, that's exactly what the S was supposed to be. So if the R is equal to X naught plus B over D times T, which is the first expression, then the S is going to exactly match the second expression. So modulo this little hiccup that I don't know that T is an integer, at least it wasn't clear to me that it was an integer. I think we're good with this. Yeah, go ahead, Tam.
Doctor, isn't it clear it is an integer because it's gonna be D over B times R minus X naught, and me will go into D because it's the greatest common divisor.
So if I solve for T,
D over B times R minus X naught.
Right, so I'll just write it like that first, it'd be D over B times R minus X naught.
Isn't D over B guaranteed to be an integer, because it's the greatest common divisor of A and B?
Well, if, let's say that actually the D divides B,
Oh, that.
not the other way around. So the D might be 3 and the B could be 6. So it actually looks like a fraction. I know, I saw that, I was like, oh, this is good, this should be an integer clearly, but I didn't think it was clear. So I don't like to write stuff down unless I can totally justify it for myself. So I would like to make it clear with this asterisk, why is it that T is an integer here? And I'm gonna do it right here. Like I said, the book didn't do this. I hate it when the book does that to me. I like the book, sorry, I like the book. The proof will be left to the reader, I don't know. I get nervous when I see that. Anyway, let's just talk about this little star point for just a second. I would like to, if I really want to know that T is an integer, I need to show, so we need to show, probably from now on, I'm gonna get lazy and write WNTS for the rest of the semester. We need to show, really what we need to show, let's just kind of remind ourselves again, sorry, I just erased it. We need to show that this guy is an integer, right? So we need to show, and actually to show that that's an integer, if I want to show that this is an integer, I need to know that the denominator divides into the numerator, right? And so in other words, we need to show that B over D divides R minus X naught. That's it. That's what I need to show. If I can show this, then I'm going to be comfortable that T really is a whole number. It's an integer in that case. Okay, so what's the little reason for this? So for this, I need to do a quick little explanation for this one. Well, guys, we already know that AX naught plus BY naught is equal to C. And we also know that AR plus BS is equal to C. Those are both true because we have solutions, two solutions. We have X naught, Y naught, and we also have R and S. And what I'm going to do now, guys, is subtract these two equations. I'm just going to subtract them. I actually think to make it look more like what I have over there, I'll take the bottom one minus the top one. So subtract, and we get A times R minus X naught plus B times S minus Y naught is equal to 0. Okay. By the way, guys, let me know if I'm going too fast. I get really excited. Well, the B, so let's see. B over D, trying to show that it divides something. It certainly divides B. Certainly divides B, and B divides B times S minus Y naught. Yeah. But B times S minus Y naught is basically the same thing as A times R minus X naught. There's a minus sign there, but other than that, no big deal. So B over D actually divides A times R minus X naught. Actually, sorry. I did one thing not quite right. If we come back to this subtraction line, I want to do, I just skipped a step I should have done, which is I want to take this thing and just divide through by D all the way through it. I can certainly just do that. That's what I should have done. No big deal. B over D still divides. You know, I just don't need this really. Right. B over D just divides B over D times S minus why not? And therefore B over D, sorry, I'm fixing my proof a little bit. So if B over D divides this part, then it also divides that part. That's what I meant to do, sorry. Okay. And so I know that B over D divides this whole thing. But I would like to prove that B over D simply divides R minus X naught. Can anybody help me? Weston? It's, I keep these things on the board for a reason, right? If one thing divides the product of two others, that's what I've got right now. B over D divides the product of A over D times R minus X naught. But if the divisor is relatively prime with one of the factors, actually, what we know is that the GCD, what is the GCD of A over D with B over D? This would have been in the lecture last week, in the notes, right? It's just one, right? Because you've divided out all of the common factors between A and B. This is just one, right? And so if the two numbers are relatively prime, the divisor is relatively prime to one of them, then the divisor has to fully divide the other part. So that is exactly right. Weston got it by the Euclid's lemma. Told you we were going to use it today. Here we have it. By Euclid's lemma, B over D does in fact divide R minus X naught, and that's kind of a confirmation that the star point is true. And because of that, then this T that we found over here actually is an integer, even though it may not have looked like it sort of on the surface of it on the paper. Yeah. Good point. Yeah, Marcus?
Oh, sorry, B already divides the top part there.
This one?
Yes, how does it divide A over D?
From this equation here, if B over D clearly divides this guy. Well, this over here is just the negative of this over here, because they add up to zero. They're adding up to zero, so this whole thing is just the negative of this whole thing. So if something's dividing this one, it's also dividing that one. Yeah, that's a good point. Good point. I love all these checks and verifications. I love all the questions. All the talking is great. You keep me honest. I can't get away with anything with you guys. I can tell already. That's a good thing. I like that. So let's just do an example, maybe like an actual problem to practice this a little bit now that we got everything justified pretty well. Yeah, that Euclid's lemma is going to come up again. This is one of those results that's like, that doesn't seem like that big of a deal, but actually comes up, is quite important. Question?
I'm gonna take a chance and ask, I don't know if it's like the notation
Mhm.
of that result kind of get it to me, but is that somehow tied to the point slope formula?
You could certainly make a connection to that, because after all, we are looking at something that's basically a line. So I would argue that there would definitely be a connection there. Of course, with point slope formula for a line, you're just writing the line in a different form. So you could take AX plus BY equals C, solve that for Y, and write that as a point slope form of a line. And it will definitely have elements of this showing up in the equation. Yeah, absolutely. Yeah, absolutely. Okay, let's try an example. Let's do an example here. It'll obviously be interesting if there is actually solutions to find. So determine all solutions to 24x plus 138y equals 18 with x and y living as integers. So try to find all of the integer valued solutions. By the way, guys, I'm really super excited about math, which means I can talk on and on. I have no clock in this room right now, so if it gets to be, we stop at 5:15, is that right?
Yeah.
Okay, I've got 15 minutes, so just keep me honest because I don't know what time it is. Anyway, so for the solution to this, obviously the solutions are involving D. You can see, so the very first thing I would recommend that you do if you get a problem like this is to find the greatest common divisor of A and B. So you can certainly do that. So we find the GCD of, in this case, it would be 24 with 138. I did one of these in my video notes, right? Kind of a Math 302 review problem where I kind of showed the Euclidean algorithm forwards and backwards.
Yeah.
Maybe if you'll allow me to just skip to the answer here. The answer is 6, and you can check that easily enough. I'll just leave out the details for that. But what you really need to be doing is writing that GCD as an integer combination of 24 and 138. So you're going to want to do that in order to find your solutions here. So notice that, so we can find by this process that I showed you in the videos that we can write this GCD, which is 6, as 6 times 24. Actually, let me write it the other way. Let me write it as 24 times 6, and then plus 138 times -1. That way, it really does look like a times x plus b, let's call it x naught, plus b times y naught. Okay. So the way that you do this is its Euclidean algorithm forward and backwards. Is everybody okay if I just write this down, or do you want me to? I can go through the whole thing if you want. This is okay? Okay. I mean, you can just check it out. 144 minus 138. But you need to do that first. Now, of course, our equation is not equal to 6 here. It's equal to 18. But remember that what you found here is going to be a divisor of 18. It has to be, because remember, there is no solution to the Diophantine equation unless this GCD divides the C value. So what you now have to do is take this equation and simply multiply it through by, I think I called it M in the proof earlier. It's just whatever C over D is, which is going to be 3 in this case. So multiply by 3. And I'll do that. I'll put the result over here. So what we're going to get over here is 18 is equal to 24 times 18 plus 138 times -3. So I'm literally just multiplying the whole thing through by 3. And now here's your, this is really the x naught and the y naught that makes your first solution. I shouldn't really call this x naught and y naught right here. We can call them, you know, x and y, I suppose. But these are really the x naught and y naught values. So we have a solution here, 18 comma -3. That's one solution to the Diophantine equation. That's the x naught and the y naught value. And so then to get all of the solutions, we just have to plug into this box thing here. So then if I want to know what x and y are, easy peasy. X naught was 18, and it's plus b over d. Let's get this right. B is 138, and d was 6, right, times t. I'll clean that up in a second, right? And the y value was -3 minus a over d, that would be 24 over 6 times t. So we just have to remember where the a and the b go and where the plus and the minus go in this write-up. And so the first one just becomes 18 plus, I think it's 23 actually, times t. So 18 plus 23t, if you take 138 divided by 6. And then the second one is -3 minus 4t. And of course, t is any integer whatsoever. So here we've actually done a physical problem that has an infinite number of solutions, and we've written them all down, parameterized by t. Parameterized by t. So it's mostly just, it's not that difficult at this level. I wouldn't think, that you can find A, B, D, X naught and Y naught and be good to go. So nice. Now on this problem, it may not be clear whether you can solve this with positive values. It looks kind of like Y is going to be negative most of the time, but maybe you can find some values of T that would give you positive solutions. And if your physical problem requires positive solutions, then you might have to limit the T values only to those that would give you positive solutions. Maybe I should write down one more problem as an example, and then this is really pretty much going to wrap up this chapter, actually. Chapter 3 is about prime numbers. We'll do that on Thursday. You guys like prime numbers? I'm going back into the prime of life again later this semester. Every year I have a birthday, it's like I'm either in the prime of life or not. No, unfortunately. As life goes on, you're in the prime of life less frequently. But so when it happens, you get really excited. So that'll be me in a few months. Anyway, where am I going? Oh yeah, another example. So this is I don't know when I wrote these notes out. I taught this class maybe 20 years ago, so the prices that I have here are gonna be a little bit low. But it'll still work. The theater charges, so we're gonna go to a movie, I guess. The theater charges $1.80. Yeah, now you're finding out really how old I am, really how much in the prime of life I'm gonna be. $1.80 for adults. And for kids, it's only gonna be 75 cents. Oh man, I wish. For children. Okay, so if the total movie profit for the night was $90, so too good. And I have to add one more thing to make this work out as a reasonable problem. Let's assume there were more adults than kids. So there were more adults than kids. The question is, how many people attended the movie? Okay, so how many people attended the movie? Excuse me. So this will be mostly just the same math we've been doing, but this time there's a little bit of a physical constraint that we'll have to figure out how to deal with at the end of this. So, but we're going to start off this problem kind of just the same way that we solved the previous example, which was sort of just a raw math problem. This one is going to start off the same way, and we'll just have to deal with the physical nature of it in a few minutes. Okay, so for the solution, I think I'll do it over here. And I hope I have time for this. I have 5 minutes. 5 minutes, that's enough time. I always say that. We'll see. So I have, let's just say we have X adults. And we have Y children. Okay, and so the first thing is that every adult was a charge of $1.80. So 1.8, right, times X would be added to every child was 75 cents. So that'd be 0.75 times Y, and this is all supposed to come out to 90. And we have this constraint that there were more adults than kids. So just to add that on the side there, we're looking for some solutions where X is greater than Y. And here we really do have a scenario where we should expect whole number values. We should not even get negative numbers here. These need to be non-negative, positive, well, just positive integer values. So it's a good problem for number theory. Now, I don't see whole numbers immediately in the coefficients here. So what do you suppose I'm going to do first? multiply through probably by 100, just to get rid of the fractions here. So this will be 180 times x plus 75 times y equals 9,000, right? So now we've got our Diophantine equation, good to go. And just like before, the a and the b are sitting here, 180 and 75. I've got to figure out how to find the GCD of those two numbers. Okay, so the GCD of 180 along with 75. It turns out that it's just 15. It's just 15. Just to show you the steps, I won't write a lot here. 180, you just divide it by 75. It goes in there two times and leaves a remainder of 30. And then you take 75 and divide it into 30. It again goes 2 times with a remainder of 15. And at that point, you put 30 here, it goes in 2 times into 15 with no remainder. So remember that the GCD is, as I talked about in the videos, is the last non-zero remainder. So that's 15. And so what you need to do is rewrite that 15 as an integer combination of the original numbers a and b. To do that, we run this algorithm backwards. Again, I'll go very quickly just in doing that part, 75 minus 2 times 30. And then we take the 30 and we replace that one with 180 minus 2 times 75, like so. And when we clean that one up, we're going to have 5 times 75 minus 2 times 180, like so. Let's get it lined up in the correct order here. So I've got my linear combination. 15 equals 5 times 75 minus 2 times 180. But let's get it in the order of the original equation. So it would be 180 times negative 2. And then plus 75 times 5. And that adds up to 15, presuming I did it all correctly. And I have to take this equation, just like before in the previous example, I had to multiply through by 3. Here, I have to multiply through, I have to jack 15 up to 9,000, I'm sorry. I have to jack 15 up to 9,000. I think you have to multiply by 600. So times 600 here, going a little quickly just because I'm a little short on time. If I multiply through by 600, I get 180 times negative 1,200 plus 75 times 3,000 equals 9,000. Okay. And so I'm going to erase the question so I can put the solution, the rest of it here. We're almost done. We're almost good to go. I've got my X naught right here and my Y naught right here. Yeah. X naught and Y naught. I've managed to keep these things on the board, which is a good thing. We're going to use that. So what is my general solution for X and Y here? Just coming to these equations, right? I put in the X naught value, which was negative 1,200, and we have to add B over D. So let's see if we can figure out what B and D are. B is 75 and D was 15, right? So 75 over 15 times T. Okay. This will simplify to 5, I believe. And then the Y value is Y naught, which is 3,000, minus A over D. The A value is 180. We're dividing that by 15. So minus 180 divided by 15 of T. And so this is just negative 1,200 plus 5T for X. And for Y, we have 3,000 minus 12T. Yeah. And the key thing here, guys, is that these need to be both not negative. You can't have negative numbers of kids. So this has to be at least 0. This has to be at least 0. And don't forget that X has to be greater than Y as well. We have that little constraint as well. So just to basically wrap this up because I'm basically about out of time. I'm just gonna figure out what conditions on T we have here. So if you just give me 1 extra minute to do that, negative 1200 plus 5t has to be greater than 0. That looks like t has to be greater than or equal to, what is it, 1200 over 5? Right? If I just kind of move this around and solve it for t, t would be greater than or equal to 1200 over 5, which is 240, I think. Something like that. And then the second equation actually constrains t in the opposite direction. T has to be less than or equal to 3000 divided by 12. And that gives me 250. Okay, so there's about 10 values of t, roughly 11 values of t, that are potentially going to make both of these non-negative. And you can start playing with them. If you try, for example, 240 for t, what will happen is x would be 0. Well, that doesn't look too good. Because if x is 0, if t is 240, you get 0. That's not too good because if x is 0, that means you have no adults. We're supposed to have more adults than kids. So that doesn't work, right? And if you even try like, okay, well, 241. Now for 241, if I plug that into here, it's just going to jack x up to 5, I guess. Yeah. 5 adults. But the number of kids, if t is 241, I needed a calculator. 12 times 241, if I subtract that from 3000, it's going to be, does anybody have a calculator? Can you just punch it in for me? I just want to know, what is 12 times 241?
2,892.
2,892. So when you subtract, you get 108. So it's still too many kids compared to adults. Sorry. So you just go through these and you quickly realize, oh, there's actually not very many of these that'll work. And you can come up with the final answer is actually that t could be 248, in which case you would have 40 adults and 24 kids. I'm gonna wrap this up quickly. This part I do have good details on. So 248 works, but anything less than that doesn't work. 249 also works. So there's actually more than one possibility here. There's more than one possible way to have this work out. This one would be 45 adults. And we'd have to now have only 12 kids. And then the last one is if t was equal to 250. Now you'd have 50 adults and no kids. So there's actually 3 correct answers that are all possible for this Diophantine equation. Yeah. Okay. Sorry to run that a little over, but just so it physically lines up with the assumptions of the problem, I wanted to spell that out. Good stuff. Any questions? What do you guys think? Making sense? Diophantine equations, they come up in the real world, except I need to multiply these prices up a little bit for my next time I teach the class. All right, guys, have a great rest of your Tuesday. I'll be heading downstairs if anybody wants to chat with me about anything. Otherwise, I will definitely at the latest see you on Thursday, and I'm looking forward to it. Bye for now.